Our next speaker is a very special guest. I'm particularly excited about this talk because I have no doubt it will be completely different to what we've already seen and what we will already see for the rest of the conference. We are passionate about technology. I'm here like a child and I'm getting to interview these people because I love technology and I love entrepreneurship. But all of this wonderful technology that we're talking about, the digital revolution, Industry 4.0, big data, artificial intelligence, virtual reality, everything else, IoT, none of this would even exist if it wasn't for the basis underlying all of it, which is mathematics. If we don't bring mathematics back, making it just as sexy as entrepreneurship, we might not have the same level and quality of entrepreneurs. And that's why we're super excited about our next speaker. Our next speaker is a Russian mathematician, the Fels Medal awardee of 1994. This is essentially the Nobel Prize of Mathematics. He has a long relationship with Spain and has collaborated professionally and with his friends here in Spain, for example, with Professor Santos Gonzalez from the University of Oviedo. And I am thrilled to introduce the next speaker to tell us what it's all really about, and it's bringing the magic back to mathematics. Efim, please, if you'd like to take the stage.
Please. Well, thank you. I have 20 minutes to say something about mathematics. And the very fact that I was invited to speak at this very distinguished forum says more about prestige and applicability of mathematics than whatever I can say. Now, I was so impressed by the previous talks that I feel like Jim Kelvey described when he had to speak after Jack Welch. So mathematics is different from experimental sciences, like physics, chemistry, biology. In experimental sciences, the criterion of truth is repetition of experiment. Whatever you claim has to be independently confirmed in other laboratories. In mathematics, the criterion of truth is Her Majesty proof. Many of you heard about the great Fermat theorem. Did anybody have any doubts that it is true? Not really. But it took 300 years to prove it, and it was a great achievement. Well, now the greatest single problem in mathematics is the so-called Riemann conjecture. Everybody knows that it is true, but that's not enough. Now I have to move it somehow. Can you? Yeah. So what's a proof? Roughly speaking, a proof is what is considered to be a proof by all mathematicians. And it is a very durable goods. The proofs that appeared in the book of Euclid 2,000 years ago are still proofs. And the purpose of the proof is not only verification that something is true. The real purpose is understanding. We want to know not only if this or that is true, we want to know why it is true. And proofs are so much detached from reality that it almost makes mathematics an art. It perfectly fits the definition given by Jim McKelvey at this podium, trying to sell something that nobody needs. Proofs can be beautiful or ugly. If you listen to a conversation between two mathematicians, it's like conversation of two artists. Some areas of mathematics appeared because of some practical problems, like calculus invented by Newton and Leibniz, or PDE, after the invention of electromagnetism, numerical mathematics, and some were pure creation of mathematical mind. They appeared as art by intrinsic logic. I want also to say that mathematics is a very strange art. On one hand, it is very elitist. Millions can enjoy some beautiful paintings. How many people can enjoy a mathematical paper? Very few. On the other hand, it is the best supported art. It is supported by industry, military. It is discussed at entrepreneurial forums. So this contradiction that mathematics is both a science and an art, by the beginning of the 20th century, it almost brought these two sides of mathematics to divorce. Mathematics kind of divided into applied mathematics, dealing with real world, and pure mathematics, beautiful, but seems to be useless. In many universities, this divorce is done formally. There is a department of applied mathematics, there is a department of pure mathematics. In other universities, they coexist in the same departments. Now, this young gentleman is Évariste Galois. Évariste Galois was killed at the age of 20 in the first half of the 19th century. He was killed on a duel. He did not have any formal mathematical education at all. He failed entrance exams to the university, but he attended public lectures on mathematics. And whenever I have to give a public lecture, I always think about Galois. Since he did not have any illusions about his ability to shoot, the night before the duel, he wrote a very detailed mathematical letter to his friend. Hermann Weyl, one of the top mathematicians of the 20th century, called this letter the most important paper in history of mathematics. Galois worked on solution of equations in radicals. Well, from middle school, you know how to solve quadratic equations, formula. There exist formulas also for the cubic equation and equation of degree 4. Very complicated, nobody remembers them, but they exist. For many years, people tried to find similar formulas for equations of degree 5, and nobody succeeded. And finally, well, Ruffini, he produced a wrong proof, but influential one. And then finally, another young genius, Henrik Abel, proved that such a formula just doesn't exist. And Galois explained the real reason why it may exist or not. He asked the right question. It's very important to ask right questions. The right question was about symmetries of roots. In mathematics, it's called groups of symmetries. And when, in the 20th centuries, physicists started to study elementary particles, they knew which question to ask. The elementary particles are distinguished by symmetries. So I heard this phrase from Sheldon Glashow, a famous physicist, Nobel Prize winner, that he said, I don't know if God exists, but if he exists, then he knows group theory. It was about elementary particles. It's amazing that roots of equations, elementary particles, and if you come to Alhambra, ornaments in Alhambra have some similar, have some similar symmetries. And that is universality of mathematics. Mathematics does not study any particular objects, but the results of mathematics are applicable to physics, to studying ornaments, anything. Please, that thing, I used it to move. Okay. And among other things, Galois invented finite fields. I don't know why he did it. You know, we all know what are real numbers and complex numbers. He invented, the beautiful properties of numbers is that you can add them, you can multiply, you can even divide by a non-zero number. Galois invented finite systems which enjoy all the same properties, but they were finite. And that was not related to his main problem of a solution of equations. So I don't know why he did it. It was just a game of a mind of a genius. When I was a student in Siberia 40 years ago, we all knew that real world is real numbers and complex numbers. And only decadent algebraists and number theorists can be interested in finite fields that are good for nothing. But the second part of the 20th century turned all tables. You know, with the development of communications, high-frequency radio, satellites, it became very important to send messages and to read them properly. A message is a sequence of zeros and ones, or more generally, of elements from Galois finite fields. When you get a message from satellite, there are always some mistakes. And you have to guess the right message. And that led to the creation of error-correcting codes. Then they were all based on Galois finite fields. In the 70s, another problem appeared, the problem of public cryptography. You know, 100 years ago, if one general wants to send an encoded message to another general, they agreed on a code, some page from some famous book. These codes were virtually impossible to break, but with the appearance of computer, a different problem appeared. Millions of people have to agree on their passwords with their internet providers. And millions of people who use ATM machines have to agree on passwords with their banks. That's a different problems. All methods just did not work. And mathematics provided the answers, and they were all again based on Galois finite fields. So each time when you use emails or use ATM machine or listen to musics, digital musics, you use non-trivial algebra, number theory, and Galois finite fields. And that's again universality of mathematics. It doesn't work. Oh, yeah. Now, this photo, by the way, when I showed you the picture of Galois, don't believe it. Nobody knows how Galois looked. He was a teenager. Nobody would bother to make his portrait. There were no photos. So that beautiful picture is a fantasy of an artist. But this is a real photo of Johann Radon, a well-known Austrian mathematician. He had a respectful career, was elected to Austrian Academy of Sciences, not like Galois, who was not recognized by anybody in his lifetime. This is Johann Radon. He published a paper kind of on inverse problems. Integration is when you know a function and you want to find its integral. Inverse problem, you know integrals, say over straight lines, please find the function. He was not motivated by any applications. It was internal mathematical logic, just a nice question. That's it. However, in 1970, Cormack and Hounsfield invented tomography, and later they got Nobel Prize for it. The tomography is entirely based on radon's formulas. X-rays, when you can measure integrals of density and then you can recover the density and get the picture that you get on your tomogram. But X-rays are not good for many patients, for pregnant women, not too good. So it is preferable to use ultrasound tomography. But X-rays are strong, they go straight. Ultrasound waves are less strong. So the wave propagates along some curves, and you get integrals of density over these curves. And there are no these nice formulas like radon's formulas. It's sort of unsolved mathematical problem. And therefore, the ultrasound tomography is less strong. So it's all mathematical problem. Another application is geology. Now I want to say about the third application, the so-called big data, starting with a quotation which is attributed to Napoleon, that God is usually on the side of big battalions, of big data. It's huge arrays of information. Which mathematics will be needed is still a bit unclear. Statistics, computer science, mathematics, because arrays are so huge that you can deal with them only through certain algorithms. So that picture of mathematics was not correct. This is much more correct. There is mathematics. It is surrounded by applications to all sides. This is a much more correct picture. Well, so Eugen Wigner called it unreasonable effectiveness of mathematics, because I want to mention that Galois, Radon, even Gene Simons were pure mathematicians. You know, the title of my talk isn't Magic of Mathematics. I did not invent this title. It was invented by the organizers, but I like it. Because whatever I tell you, whatever explanations other people give you, there is still some magic. Now, I'm not calling on everybody to become mathematicians. Jim McKelvey said that he cannot stop thinking about mathematics. Well, not to that extent. But some understanding of applicability and, what is very important, of limitations of mathematics might be useful. Thank you.
Amazing, Efim. Thank you so much. Excellent.